So thanks everyone for coming this morning. I think we'll have some other people that are filtering in, but I thought to give the full hour, we'd go ahead and get started this morning. And I know almost all of you, but a few of you may not know. And my name's Greg Cooper, and it's my pleasure to introduce Dr. Jonas Peters as our distinguished lecturer today. Dr. Peters is an associate professor of statistics in the Department of Mathematical Sciences at the University of Copenhagen. He completed his PhD in 2012 at ETH in Zurich with Peter Buhlmann as his thesis advisor. His dissertation was titled Restricted Structural Equation Models for Causal Inference, and he won the ETH medal for an outstanding PhD thesis. Dr. Peters then worked as a postdoctoral fellow at ETH for about 2 years, and during that time he visited the Department of Philosophy at CMU for several months with Peter Spirides, I believe, serving as his host in about 2013 or so, 2014, 2013. 14, okay.
The World Cup.
Oh, okay. Yeah. Okay, that's something. It's an anchor to remember by. In 2015 and 16, Dr. Peters was the group leader for the Causality group at the Max Planck Institute for Intelligent Systems in Tübingen, Germany. And then in 2016, he joined the faculty at the University of Copenhagen, as I mentioned. He's published extensively on causal modeling and discovery in numerous places, journals, and in conferences that we all know well, AI Stats, ICML, NIPS, UAI, and he's also, I think, it significantly is the first author of a causality textbook with Dr. Janzig and Skolkov, which was recently published by MIT Press, and is titled Elements of Causal Inference, Foundations, and Learning Algorithms. I think that was published in 2017, just last year. In general, Dr. Peters' research focuses on theory and methods of causal discovery from either purely observational data or from a combination of observational and experimental data. And today's talk is titled Invariance and Causality. It's a great pleasure to have him here, and I hope you'll join me in welcoming him. Thank you for being here.
Thank you very much. Thank you for the kind words and also for the invitation. Thank all of you for coming here. So for me, it's really a pleasure to be at CMU. I feel very honored to be invited to this place. It's a very remarkable place and pretty unique in the history of causality. I think that's certainly fair to say. The work initiated a lot of thinking that causal search can be actually possible under certain assumptions. And I think we are all building up on these ideas. Today I would like to talk about invariance and causality, and I should really say that this is joint work with a lot of people, Christina Heinze, Rune Christiansen, Nikolai Mainzhausen, Niklas Pfister, Dominik Rotenhäusler, and Peter Buhlmann. It's a combination of people from ETH and from Copenhagen. So I'd like to just jump in. So this is as all of you know, I guess, this is a way of describing what we are trying to do in causal discovery or causal search. So we observe some data, and here I write down IID data, but of course in practice we often have more complicated data structure like this. You can think of just a data matrix, and then a goal would be to understand what is the underlying causal model, and there are various ways of writing down what we mean by a causal model, but one way is to write down a directed acyclic graph, in short DAG for G. Now you can say that this is a problem that is really aiming high, but I would say that aiming for something high is something that has always been doing in this department, and maybe to illustrate this, nice picture that I was able to take 4 years ago, and I would say that people here were very successful in aiming high, although I don't mean I don't mean like this particular case, but of course the scientific part that was very successful in this department as well. Good, we are not aiming that high, we are doing
Can we all get a copy?
I'm not so sure. I was asking whether we Okay, so speaking of aiming high, we are not doing this here in the talk. So we are aiming for something much lower. And I will try to also argue why this comes with certain benefits. So what is the setting we are considering here? We are saying that we may have a situation where we have a target variable, let's call this y, that we are particularly interested in. And we are not trying to infer the full causal structure for now, but what we are interested in is finding out if we have a bunch of predictors, can we find out which of them are the causal predictors? So if you look at this graph, then you will find out, I mean, it's known under the name of Markov blanket, right, that many of these variables, in fact here, all of the variables will be very good predictors for y. But only these two will be the direct causes. And the goal for this talk is to find out, can we somehow infer which of these predictors are the causal predictors? So that's our goal. You happy with this? Otherwise, just interrupt at any time. I think it should be interactive here. Good. So, I mean, all of you know this. I nevertheless would like to show you this again. So some people, and you still read this often, right, is that some people say, well, maybe the causal predictors are just the best predictors in some ways. So if you have a target variable, and this is here some yeast data, where you have expression levels, this is one gene that might be your target, and maybe you say, well, I just look for all predictors. In this case, we have 6,000 measurements of 6,000 other genes, and we just go for the strongest predictor. And here, this is what we see plotted here. This is the gene that actually has the strongest correlation with our target. Is this a causal predictor? Yes or no? And we are here, we are lucky to be able to answer this because we have some interventional data as well, where people, not us, the biologists, have actually intervened in the system and have deleted this gene. So I will show you in a second now an additional data point where this gene is not there anymore. So it's deleted. So what we expect is that the activity of this gene will go down. So here, this is the additional data point that you see. So what you see is that the activity, as I said, goes down. This is good because the gene is not there anymore. And now if you look at the target gene, it actually does what it always does, right? So it lies in this region here. So what can we conclude from this? Well, it means that this is certainly not a causal predictor because we are intervening in the system. We are sort of deleting our predictor and we don't see any response in the target. So there's no sign, at least, that this is a causal predictor. What's the way out? Well, Chuck Norris is using the invariant causal prediction idea. And this is something that I would like to talk about for the next 10 or 15 minutes or so. This is now something that will be a bit vague. I tried to make this a bit more precise later. So one way of phrasing this, so if you think about what is the underlying idea that will guarantee some identifiability of the causal structure, and this I would like to describe with what we nowadays call an anchor. So we will choose an anchor and we will find invariant models. And this may not make a lot of sense now, and I hope it will make more sense when we talk about a couple of examples. So what do I mean by anchor? So the first thing that we're looking at are what we will call two different environments. So this will be our anchor for identifiability. So we have an unknown causal structure that is underlying our system. And again, we have our target variable here, and we have a couple of predictors. And now this is what we assume. We assume that we are given not only an IID sample of the underlying joint distribution, but we are actually given two IID samples of the underlying distribution. So let's call this the blue environment and this is the orange environment. They are both sort of simulated from this underlying structure, but now with sort of different interventions. So this is the assumption. So we are given a data set, a blue data set and an orange data set. Now, if you plug this into a linear model, and this is basically the same statement as I made before. So if you just ignore causality, then what you would find is if you run a linear model, so you just regress y on your three predictors, then this is an R output. What you would find is something like this. You would find that all of these random variables are very good predictors. They are highly significant for y. I go back one slide so that you can see the model again. This is not surprising, right? So all of these variables contain a lot of information about y. Now, what we are proposing to do is this what we call invariant causal prediction, and it's not only an idea that exists as a theorem, but also as a package. So this is what the package will do. So it actually looks a bit like a linear model, but now we have to provide one more thing to the method, and this is the index of the experiment. So this is the indicator that tells you which environment am I in. And this is just, if you can think of this as a vector. So if you have 600 data points, maybe the first 400 data points are from environment 1, and then the next 200 from environment 2. This is all what we provide to the method, and this is something that you may find out. So here, indeed, the method is able to identify x1 and x3 as the direct causes, and x2 not. So this is the goal that we are trying to achieve, and I would now like to explain what the method actually does. Surprisingly simple. So, but this is what sort of the outcome of the method is. Okay, here comes the idea, and the idea again, so this is now one slide, but if you want to take away anything from this talk, then it would be nice if it's this slide. So if something is unclear because I didn't explain it well, please ask. So the underlying assumption is something extremely fundamental. So what is this? So again, we have these two environments, the blue and the orange environment. And now imagine now for a second that we have an underlying structure that is unknown, and that the environments were constructed by interventions. So here in the orange environment, we have the same graph structure, but now we have an intervention on x1 and an intervention on x2. So now the joint distributions in the blue and the orange data sets will be different. But there's at least one thing that remains exactly the same. And this is the conditional distribution of y given x1 and x4. So in both of these environments, the conditional of y given x1 and x4 will be exactly the same. And this is the fact if you do anything that you like in this orange environment except for intervening on y. This is an assumption that is, I mean, it sounds a bit trivial, but this is quite fundamental, and this has many different names. So modularity or autonomy are just two of them, and this is was extremely well understood, I think, already in the 40s. So Havelmo is only one name. There are some others. This is the Cowles Commission work. If you read these papers, they understood quite a bit of this. And it looks a bit like an innocent assumption, but I think it's quite fundamental. So it means that if we are changing some part of the system, we are assuming that other parts will remain the same, right? You can say, well, this is maybe trivial, but if you think about examples, I think it's not so much. It's really an assumption, and in many situations, this makes sense. So if you think about even drug treatment, right? So the question is whether an aspirin works or not. Does it actually depend on how we provide it to the patient? And at first you may think it does not depend the way, but then you have the placebo effects and so on. So this is actually a non-trivial assumption. But this is the assumption that we are using here. How do we use it? This is now very simple. So we will go through a lot of possible, we turn this principle around. We are saying, well, if we are now given data from the blue and the orange environment, we're actually searching for these invariant models. So how do we do this? We go through a candidate model, let's say the model that just has 2 as a predictor, and then we want to check, is this an invariant model? And how do you check? So this is an example. One way is to just plot y against our predictor, x2, and see whether it's the same model in the blue data and the orange data. And here you see it's not. This is a no answer, right? Because the regression coefficients are actually different. So here we see that, well, 2 is probably not a causal model, right? Because the regression coefficients differ. However, if we would have the correct causal model, then they would not. Now, what do? We suggest to go through all possible candidate models. In practice, you can be a bit smarter than this, but in principle, you go through all possible subsets, and you always check, do I have this invariant prediction, yes or no? And in the linear case, you can think about, is it the same regression coefficient, yes or no? And you will get a lot of no answers. This is the example that you have seen before, and you get some yes answers. And then we suggest to do something very simple. You just go through all the yes answers, and you take the intersection. So you're outputting the variables that are really necessary in order to get an invariant model. And in this case, it would be, for example, 1 and 4, and then you would be, of course, very happy because this is the correct set. So now, what do we know about this procedure? So we know that certainly, by assumption, the correct causal set, that we don't know, but this will be one of the yes answers. And now we are taking intersections. We are taking intersections of a lot of sets, and one of them is the true set. So what do we know? We know that with very large probability, our estimate will be a subset of the true set. And this is what you can prove, and this is just what I wrote in small letters here. So with large probability, your estimate will be contained in the set S star, which is the true set. And this is all of the underlying ideas. So I would say it's rather simple. So you assume you're given data from different environments. You just go through all possible sets, always check, do I have this invariance? And then I output the intersection. Are there any questions about this? Is the procedure clear? So there are many things that I didn't tell you. For example, how do you test? Right, but this I leave aside for a second. So there are a couple of different tests. One easy way is to say, well, you just pool the data with a joint regression, and then you check whether the residuals differ in distribution. One way, there are many other ways as well. Yeah?
Are you making any?
Very good. So this is exactly the key question. What we are assuming, and I will be a bit more precise on the next slide, we are assuming that we have an idea about the model y given x1 and x4. So meaning that to be more precise, y given its causal parents. This is the part that we are modeling. The rest we do not model. And I said that before, we have sort of our goal is a bit less ambitious, right? We are only trying to find causal predictors. We are not trying to find the full causal graph. But this comes with a couple of benefits. One benefit is that indeed we do not have even to model the rest of the structure. So we don't care. So these x's can be anything. They don't even have to be IID. They may be cycles, hidden variables, whatsoever. The only part that you have to model is y given the parents. And this, of course, is also the hard part. But this is underlying. Yeah, so this is the question. There's another good question. So here we are assuming this invariance, right? So we are assuming that you do not intervene on the target. So hopefully, if this is now confusing, then
I'm not intervening on the target, I'm saying.
This is about hidden variables. Yeah. So there are two answers to this. One is, if you have, for example, a hidden variable, then, or like if you have a model misspecification, it's a similar thing than having an important hidden variable that you miss. Then what usually happens is that no set will be invariant. So you are right in that our assumption is violated. But you can actually show, even like mathematically it's not so hard, you can actually then show that in these situations usually you expect that all the models will be violated. So what you get is that you get all no answers here, and then the output will be the empty set. So in a way, this is a built-in sort of robustness guarantee in the sense that if you're missing something very important, or have a model misspecification, you're actually not giving out, like the method does not provide you with anything useful, but at least nothing wrong as well. Because it says, well, it seems that I have been missing something important. Having said that, if the hidden variable is actually, it's a nice example because you said that batteries are either full or empty. So we are now currently working on with Rune, and this seems to be working fine, in an extension where we are allowing a binary hidden variable. So a hidden variable, if it has very like a small number of states, you can actually incorporate this into the model because you can still estimate it. If it's arbitrarily complex, the hidden variable, and it has an arbitrary influence on y, then you are lost. You cannot do anything. But
as long as
yes, so if, for example, the hidden variable is additive, it shouldn't be a problem. Yeah. But if it's more an interaction, more complicated, then you might run into problems. And then you usually, and this is also what you see in practice, if you're running a really bad model, then usually you will get the empty set out. Yeah?
So, how do you know?
Actually, so this is what I like about it. You don't even have to specify what your interventions are, right? So you don't care about what the environments are. Basically, it can be super fat-handed, and it can, if it like hits on many variables, usually there's a lot of signal in there. So this is what you would like. A problem occurs only if you're intervening on y. But then again, it's the same as before. Then you would assume that nothing is invariant because you cannot block this intervention away in a way. So then you would again get the empty set. But apart from this, a fat hand is actually something nice. So this is you really only provide the environments to the method, and you don't have to specify what they are. If you allow me, I come back to this question in a second when we talk about the gene data.
Causes, right?
But then these are situations where, and this can also happen, that everything then becomes invariant, right? This could be the other reason. So imagine that y doesn't have any causes, and you are intervening, let's say, downstream of y, then everything, or like many different sets will look invariant. Also, the empty set will look invariant, and then again, you are outputting the empty set, which in this case even is correct. Yeah.
Right. I mean, so the fact that you can
Does not
that
mean
it's incorrect.
it can. It actually. This is a good comment because we are not distinguishing this in the output, but actually there are two reasons to get the empty set. Right. This is what you are hinting at. One is everything is rejected. This tells you something. Probably my model assumption was wrong, or I was missing something. The other reason is that the empty set is accepted, so everything looks invariant, for example. And this is indeed another reason. We are a bit ignorant about this, but it's actually something that we output as a text, but there's something to do maybe. So. Because we are throwing away information, I agree. Yeah, but one has to be a bit. I mean, okay, I agree that you could do something. One has to be a tiny bit careful about these guarantees that you get, right? Yeah, this is true. One can, one can incorporate more ideas there. Yeah, I agree. Good. I'm now saying the same thing, just a bit more mathematical, but it's really the same thing. So here, this is our situation. We are getting data and environments, and our invariance assumption for a set S is really to say that y is a function of x, s, and it's always the same linear function. For all data points, it's the same regression coefficient gamma. And here, this is the linear situation. The noise variables are IID, so it's always the same noise distribution. Xi, I mean, it can have an arbitrary distribution. We are not even modeling this. And then what are the environments? So you can think of just, I don't know, maybe 3, and you just have the first 40 data points, then 60 more, and then n minus 100 more, and then we are outputting the intersection. So this is our estimator. So this is the formal way of writing this down, and the invariance assumption is really to say that there is a set S star that is satisfying the invariance. And as you commented on, there is an extension to hidden variables. I can talk a bit more about this if you are interested also afterwards. But here, this is the invariance assumption that there is a set S star that satisfies this invariance assumption. We often assume, for example, that these are the direct parents. And then, this is our guarantee. You just have that with large probability, you are a subset of this S star. And maybe as a comment, I mean, so this is a tiny first step, but I have the impression that results of this type are actually useful in practice because, I mean, of course, we have been working on graph estimation as well, but if you have 6,000 variables, I myself, I'm not very confident that at least in the next 3 years, we will have methods that can estimate the correct graph for 6,000 variables, whatever this means. So I have the impression that whenever we find something that gives us a confidence about which parts of the graphs do we believe and which ones are we a bit more uncertain about, that this could be very helpful in reality. And this is one attempt to address questions like this of significance. So here, as I already mentioned, right, so if you have the empty set, then this can have many reasons, but maybe the source of identifiability, namely the heterogeneity, is just not strong enough. And then you're saying, well, I don't know. However, if the method outputs something, then you are pretty certain that this is correct. And just this is a trivial implication, but I think it's nice to think about. So here the identifiability improves if you have more and stronger interventions at better places. Of course, you can analyze this a bit. I'm not doing this here. And if you have in general more heterogeneity in the data. It's a bit different from what we used to think, right? So having clean data, a nice, clean and homogeneous data. But here actually we employed the heterogeneity. That's the main point here. Does it work in practice? Well, I don't know. So we saw some data before. So this is now, if you apply this principle, this is again a gene data set, and we have 2 different environments, the blue and the orange data. And here you again have the same target, but now you have a different predictor. And this is now a predictor that is output by our method ICP, because this is now a predictor that satisfies this criterion that in both environments it's exactly the same linear function. And again, you can ask, well, is this a true hit? And indeed it is, because here we are intervening on the possible cause, and you exactly see a response in the effect as well. And this is true for the first 4 sort of most significant pairs in this data set for our method. It's of course not, we are not saying we are solving the problem, but we are saying this is of course significantly way better than chance, because we really have 6,000 possible genes that we choose from, right? But we are saying that this principle might be actually helpful. Two comments here. So we are using linear models, and I show a couple of extensions in a second, but here it seems to be reasonably fit. So we were surprised about this. And the other one is now about this fat hand. What is the orange data? Sorry, the blue data is observational data, and the orange data are different interventions. And you actually know what the target is, right? But we are ignorant about this. We are not even telling the method what the target is of this data point. This data point, this orange one here, this corresponds to one specific intervention. We are not even telling the method. And you can say that maybe this is an advantage because of target effects. Maybe you just think that you're intervening there. Maybe in some situations you are not so sure. So here we are just ignorant about this. I think it's even a gene deletion, yeah. Yeah, I mean, I'm skipping a few details of the experiment. You have to be a bit careful that you're not cheating, right? Because using the interventions here, but we tried very much to not cheat, so I'm confident.
That was completely very. That case, it violate your assumption that the network.
Yeah, so in some situations I agree. So there you would expect the violation, but then again, this comes to our rescue, right? Then you don't find any invariance, and this is what you see in practice. I think I'll skip about more details on this experiment because I wanted to give you a bit of an idea of what you can use with this do with this principle. So now this is in a way it's a trivial extension here, but you can also say, well, what happens if we don't have these environments, right? You can use time equally well. So you can then ask, well, maybe we are interested in models that are actually invariant over time. And this was motivated by a problem that you'll see in a second. So the idea really is exactly the same. So here, now what you see is you see an example of a non-invariant model. Okay, so this is now a model that is not invariant over time. So what do you see? Here we plot the residuals and we plot them over time. So we now have a time ordering of the variables. And what you see is that you have these jumps, for example. So these jumps mean that you actually something changes in your model, right? So you suddenly have your jump in the residuals from even a mean shift. But now, because we talk about over time, so this very much looks like before where we have three different environments. But now, because we're talking about time, you can even look at violations of invariance that are more smooth, something like this. Or you can even have violations by looking at higher orders, like the second order of the residuals. So again, these are violations of invariances. And we would say, I mean, if you look at a model, you're fitting a model, and you see that your residuals look like this, then somehow I think most of us would agree that it seems that we are missing something, right? It's not like there seems to be something that is somehow something seems to be wrong with our model. And wrong, what does it mean? We would just say, well, it's not yet fully causal, right? So this is really the underlying idea. What can you do with this? So and I'll give a couple of details. So the testing procedures is, I mean, you can construct blocks in time. Maybe I show you a real world example. This was also a motivation why we looked at this. This is now an exchange rate between Swiss francs and euro. And I like this example. This was done by Niklas Pfister. I like this example because actually I was living in Switzerland and I still had some money, not much. I didn't become rich, but I had some savings. And for a long time, the exchange rate was fixed by the Swiss National Bank to 1.2. So I thought, well, it really doesn't matter when I transfer my Swiss francs to euro. And I remember this well because I transferred this on a Thursday. This was, I think, here. And on the Saturday, suddenly I should have waited because I lost like 20% of my money, because then by surprise the Swiss National Bank announced that they don't keep the exchange rate fixed anymore. So it looks a bit like I did some insider trading, but the wrong way somehow. I don't know. But this is why I remember this day very, very well, actually. So now what you can ask is, well, can we actually find in which way do you influence this course? And these are the predictors that we looked at. And I mean, you may know these data sets better, or like these situations better than I. I'm not an econometrician, but what are the variables? So this is the exchange rate in euro to Swiss francs. We have monthly data, and now we have a bunch of predictors. And so, long story short, so what we expect to pop up as a causal predictor is, for example, this one. These are the foreign currency investments of the Swiss National Bank. And this is, of course, how a national bank tries to influence the course, right? So if they want to support the euro, then they, of course, buy more euros. And then we also saw that the Swiss GDP, for example, we will see that this also pops up, and maybe this is not such a bad idea or bad result. And I'm showing you now, again, two models that you would find that are, one is a very bad model in terms of invariance. So this is you see on the left-hand side, and here you see that there seems to be a change in the residuals again, right? So this is something that we would like to reject, whereas this is a very good model where we do not reject the invariance, where you have sort of the distribution of the residuals is more invariant, so to say, over time. And again, I would like to stress that we are not saying this is the end of the story or whatsoever, but of course not. But somehow one is shifting the focus a tiny bit from just very good prediction that is looking for a very small residual sum of squares to one that is invariant over time. And this is really what we are stressing to an extreme here. Okay, so this is what you would find. So now on the y-axis, we have for different variables something that is extremely complicated, is a p-value for non-causality. So what does it mean? If the value is very small, the method is pretty certain that it is a causal variable. And if it's large, it doesn't know. On the x-axis, you see the number of lags, because this is, of course, dynamical data, so you have to introduce time lags as well. And now what you see is something that we were happy about, because now what you see is that if you change the number of lags, then for a certain number of lags, you actually find that there are two variables that pop up, and these are the x2 and x7. So we were happy to see that. But now this is, I think, interesting. If you go to lags that may be too high or too small for the data, then actually you remain invariant. You may remain ignorant and just output the empty set. Nothing seems to be causal. And this is, again, going towards the question of model misspecification, right? So maybe these are areas where your model is actually wrong, and then what you will find is that you don't find any invariance. Any questions about this application or this idea? I mean, I know that I'm skipping a couple of details. We tried to carefully write them down, of course, but the idea is to show a bit what you can do with this invariance idea. There's one more idea that I would like to stress, because this is also, I'm a bit sloppy here with references. Of course, there exist many works that are close, and I would like to take the opportunity here to mention at least some of them, because what you can also do, and maybe you have guessed this already, is if you're not given an environment over time, what you can always use are variables that you are certain to be non-descendants of the target. You cannot do, I mean, one has to be a tiny bit careful. So you can think, well, maybe I can cluster my data or something and use the cluster index as an environment. This does not work in general. But if you have a non-descendant of the target, then this is something that you can actually exploit. So to be more specific, what do we do? This is a third example that I just briefly mentioned. This is some fertility data from the United Nations. There, our target variable was the total fertility rate in a country in a given year. And you can be wondering, well, why is it actually that in some countries women get so many more children? And there are, of course, a couple of hypotheses that exist in social sciences. So here we have a couple of important predictors. So this is the infant mortality rate, or the under 5 mortality rate, or education, or GDP, urban population, and so on. And now here comes the trick. So in this study, this is mainly done by Christina Heinz-Demel. So here we are using the environment variable, or the environment, we are choosing the anchor or the environment to be the continent of the country. So we are saying that if we have a model that seems to be working very differently in the different countries or continents, it seems like we have missed something, right? So it seems like we have not understand the full causal relationships yet. So here, this is a variable that you can choose, and more formally, it's a non-descendant of the target variable. So we don't expect that the fertility rate is actually causing the continent that you are in, but it's, if anything, it's the other way around. And now, what can you do? This is now, I think, nice because it relates to also a lot of existing methods here. So there's a different formalization now of the invariance principle. Before we looked at linear models, but now you can also look at it this way. So we are given, this is now our anchor, our environment. We are given some data. And now what does the invariance mean? Before we said that the linear model from y on x should have the same coefficients in the different environments. This is just a more general way of writing this. So we are saying that the conditional y given xs is independent of e. So it's always the same model in for different values of e, so for different continents. And this is just a different way of writing this invariance. It's e is condition independent of y given xs. And this is also where you see, I think, that it relates to some methods also by Kevin Murphy, or I mean, Kuhn has also some work in this, many others as well, BY. So this is, of course, something that a lot of people try to exploit, right? Even in constraint-based search methods where you're saying, well, if I know that one of the variables is actually a non-descendant, I can try to exploit this, right? So for example, you see immediately it gives you a lot of more V structures and so on. The difference, what we are sort of proposing to say is that, well, if you're focusing on a local part of the graph, if you're not estimating the full graph, you actually don't have to specify the distribution of xs, and also it comes with certain guarantees that I tried to highlight earlier. This guarantee that whenever you output something, it's with large probability contained in the true set. So now, but if you formalize it like this, of course, what do? You just use your favorite condition independence test, and then you even have an extension to nonlinear data. But it's really the same idea. It's the same invariance idea, but now you can also use it for nonlinear models. Tiny bit of a watch out. I've mentioned this like 1 hour ago already. So there's actually no non-trivial condition independence test in some way. So in the following way, so if you want to test this, then actually it turns out that this is an extremely hard statistical problem. So if you have a test that has the correct level, you can actually prove that then you will not have power against any alternative. So this is a very strong statement, but from a positive perspective, what it means is that you have to be somehow, you need an idea how this conditioning looks like. So you need to be able to say, how does y depend on the xs? Otherwise, there's not a meaningful way of testing this. And this is what brings us back, right? So in a way, we are saying, well, this conditioning here, this y given xs, this we assume to be simple. Either this or the way how e depends on xs. But we have to include some simplicity assumption here. This is just maybe a word of caution, like whenever you want to use condition independence tests. Okay, but this somehow, I think, relates to the intuition that we had that you really have to have an idea about this model here. What is y given xs? And I would say that if you're in a situation where you have no idea what this model can look like, then this is not a good method to use. So this is the only part of the data that you have to be able to model. Otherwise, we don't know what to do. But I mean, the rest you don't have to model, but this part you have to be able to model. And this, I think, fits with this statement here that condition independence testing otherwise is also not possible. Good. What does it mean for the data? What you see is that you actually don't find, you get the empty set out. So the method says nothing useful. But now if you look at it more closely, what you would find is you actually see that there were 3 different sets that were obtained as invariant sets. And if you look at them, there's something interesting popping up, namely the following. So the first set that was invariant is Q5. This is the under 5 mortality rate. And in the other sets, what you would find is that there's always this IMR, and this is the infant mortality rate. And now if you look at the data, you see that the IMR and the Q5 are extremely strongly correlated. So here the method somehow cannot decide whether to put in IMR or Q5. But you can also now either say, well, I don't know, or the alternative is to say, well, we are pretty certain that it's either Q5 or IMR. So this is a statement that you can do. This is known in literature under the name of defining sets. This is not something that we invented, but this is an outcome here. And this would be the outcome of the method, right? So that says, well, how many of your kids die? It's actually, I think, a sad statement, but this seems to be in the data, at least, you really need to include this information, how many of the kids die, in order to get an invariant model. So this is the infant mortality rate or under 5 mortality rate that is suggested to cause the total fertility rate. Good. You can also do these games. Skip the details because there's one last thing that I would like to talk about. You can now ask, well, for a certain country in a given year, how would the fertility rate react if I now change, if I were to intervene the IMR and Q5 at the same time. So here, if you go to the left, ignore the colors, just think about the union for a second. If you go to the left, it means that you are decreasing the infant mortality rate or Q5 by policies, and what you would find is a confidence interval that predicts how much does the total fertility rate decrease. And you see that it decreases, so there's negative, but it's huge error bars, right? But at least this is an answer to a question of a policy intervention, right? And I would say that in many situations, this is actually what we are after at the end of the day. We want to see how does the system react under sort of an intervention. And I would argue, I mean, of course, there are some underlying assumptions here, but I would argue that it would be very nice to have these confidence intervals. Any questions about this? Now that I'm showing a couple of different examples, the idea is really to trigger some discussion. Yeah.
Let me see if I understand. The infant mortality rate, not the absolute, influence the not first.
Vice versa, we don't make a claim, actually.
I'm sorry, say again?
We do not make a claim about the other direction. So this is also, there can be some cycles as well. We don't know. The only thing that we are predicting or we are estimating or inferring is what are the causal predictors of our target. So we don't make a claim about the other direction.
But you could have run it the other way.
Yeah, we didn't. So there's one obstacle with this. I mean, the idea of saying, well, can you run it now for different nodes, is that this assumption of not intervening on the target, right? I mean, okay, the short answer is we haven't looked at this. I think something can be done. We haven't done it yet. Yeah, this is what we are trying to depict. This plot is unfortunately, I mean, I didn't explain all the details. So what do you see here? This is really a quantile. So what we have to do, because our method does not know whether it's infant mortality rate or Q5, what we have to do is we have to change both at the same time to get a meaningful result. So what you see is that you change both at the same time, and here we are not saying in absolute numbers, but in quantiles. So if you change it, so this is actually the observational point. So let's say if you put both of these values of IMR and Q5 to the 20% quantile, the lower 20% quantile, then this is the confidence interval. So then we are saying we are expecting to see a reduction in the logarithm of the total fertility rate in about a value between minus 0.5 and 1.2. This is the output of the graph. It's a very complicated plot, I agree. What I wanted to show is, yes, you can answer this, but the intervals are quite large here, the confidence intervals. Good. So if you allow me, for the last 3 slides or so, I would like to talk about one last idea that I myself, of course, I'm very biased on this, but I myself think it's interesting to look at. Because what have we done now? So it's a bit of a game that we are playing here that focuses a lot on this invariance. Why? Because we are after for causal discovery. So now if you think about why would we like to have the causal predictors? Because then we can answer these questions. What happens under a certain intervention on these causal predictors? What happens to our target? Now, if you have the causal model, you are actually able to predict the response after arbitrary interventions, after arbitrarily strong interventions. There's now a way to say, well, maybe we are not interested in arbitrary interventions, because imagine that you observe a system over time and you see certain changes in the system and maybe even certain interventions. Maybe you don't want to look for extreme interventions, but maybe you want to use what you have seen before as sort of an idea of how strong you like your interventions to be. So what do I mean by this? There's something that I would like to, or we would like to call anchor regression. And this is now changing the objective a bit. We are not only, so we can say, what happens if we are not only interested about invariance, but also at prediction at the same time? And this is something that you can trade off now. So we are proposing to find a trade-off between invariance with respect to an anchor, and this can be, again, right, time or environments or a non-descendant, doesn't matter, and predictive power at the same time. And the motivation is really that in a way, this causal discovery is, of course, very nice, and we are working on this all the time, right? But in a way, it's also restrictive, because you're saying we want to know, we want to protect ourselves, our predictions, against arbitrary interventions, right? So if you have I don't know, if you include an effect into your model, and then in the test domain, you actually have an intervention on the effect, then your model is wrong, right? So you're predicting that also your target will change, although it doesn't, because it's just an effect. However, if you have, if you're observing a system and you have never seen an intervention on this effect, maybe then you would say, well, I don't expect an intervention in the future, so maybe I want to keep it in. And this is the sort of the motivation for this anchor regression that tries to trade this off. Is this a new thing? Sort of. It's related to instrumental variables, because there we are in a way doing the same thing, right? Or a similar thing. So imagine you have this classic example, tax causing smoking causing lung cancer, and now we are interested in the causal coefficient alpha. So now, what is the idea of instrumental variable settings? If we now just regress lung cancer on smoking, then we are not happy. We know that this will not give the correct result, right? So this is standard textbook. One way of looking at this is to say, well, why is it actually wrong? It's wrong because it's not invariant. So if you look at the residuals, let's say alpha hat is just the ordinary least square solution. You just regress lung cancer on smoking. If you then look at the residuals, they will not be independent of tax, right? So we would, another way to phrase this, the same thing, is to say, well, this would not be an invariant model. It would be very different for different taxing policies. Now, what you can do is you can choose an anchor. So we can use just tax, is usually called the instrument, but you can now also call it an anchor. And now here's what we are trying to do. We want, again, instrumental variables focus only on invariance, right? So the only thing that you're interested in is to make this as invariant as possible, and this gives you the causal coefficient. And why are you interested in this? Because then you know how the system responds, no matter what the tax is. And we are saying you can also try to trade this off, and this is how you could do it. This is one way of doing it. We are suggesting a new parameter estimate, this B gamma, and what is it? So it's now a trade-off. So we are here looking at the residual sum of squares. So this is just our target. And we are looking at how well are we in prediction. And then what we are saying is this is one way, and I would say it's not a perfect way, but this is one way of looking at invariance. So let's see what this is. So here for a given B, right? So this is our regression coefficient. We are looking at the residuals, and we are checking how much does it correlate with the anchor, with the instrument. If it correlates, it's a non-invariant model. This is bad, right? So we want this to be small. If you now look at what invariant, maybe this is the easier way to start with. If you set gamma to 0, so gamma is now trading off these two paths. This is prediction. This is ordinary least squares, if you like, and this is just invariance. So now if you set gamma to 0, you just have the prediction error, right? So then you get out ordinary least squares. If you set gamma to infinity, however, what we have is we have the instrumental variable setting, because there you only care about sort of the invariance. So basically you set the instrumental variable sets the correlation between the empirical correlation between the instrument and the residuals to exactly 0. And what we are proposing to say, well, maybe you can trade this off. So you can solve this. It's not surprising. There are different ways. So one way of looking at this is to say, well, if you look at the dual, this basically means you are minimizing the residual sum of squares subject to the constraint that the empirical correlation is sort of less than a certain value. And this is just a quadratic program with linear constraints, so this is easy to solve. So what does it do? So here, this is a picture that you see. So now let's first look at the x-axis, and I say in a second what the y-axis is. So here, what you now have is you have an interpolation between the instrumental variable setting and the ordinary least squares. So this focuses only on prediction, and this only focuses on invariance. And now this gives you a sort of a whole bunch of solutions in between. You can be wondering, well, is this useful or not? And I don't know, this is up to discussion, of course. But what you would see is that it's actually useful if you sort of look at a certain kind of interventions. And this relates to the motivation that I said earlier. If you see a certain kind of intervention and you expect that this gives you a bit of an idea about what to see in the future, then this is actually exactly what you should be doing. So here we see the mean squared error under a shift of x that you actually also have seen in the training data. And this tells you that in some situations, so if you only are interested in not arbitrarily strong interventions, but interventions that we have seen before, then actually you shouldn't be doing IV and not OLS, but you should be doing something in between. And then, I mean, this is of course very hand-wavy, but you can actually see that different levels of gamma, and hopefully this is a bit of intuition at least, different levels of gamma will protect you against different kind of interventions. And this is something that you can try to analyze. What is the hope? The hope is to have maybe an idea to say, well, if we are seeing a certain sort of variation in our data, then maybe if we just look for prediction, it will not generalize well to new situations. So because you have a covariate shift or whatsoever. But maybe the causal way is also a bit too conservative, because the causal way really protects us against all kinds of interventions. So the hope would be this, the goal is that maybe with this way you can come up with prediction techniques or even regression methods that will sort of generalize well to new situations. It's adding, if you like, it's adding a bit of causal thinking into prediction. Okay, again, I know I hope I didn't offend anyone. Of course, there are relations to existing world, and this is in this paper. So, good. This is what I would like to conclude with. So, my argument is that we often know what our model should be invariant against. Not always, but we often do. And this I would propose to exploit a bit more, maybe. And then, I mean, in this very sloppy way, invariant models relate to causal models. I tried to make this more precise with the methods that I showed. This is a provocation. So is this maybe even a better notion? I mean, I don't have any theory about this or anything. This is a provocation. So it says maybe the invariance idea is maybe even better than defining causality by saying what happens under an intervention. Because maybe if you have random variables that you can never intervene on, what does it mean? So if you have a strict definition of a causal relation, you can say, well, we cannot talk about causality. But maybe if it's identifiable by other interventions in the system, maybe then we again can talk about causality. So this suggests that maybe this invariance is actually something that at the end of the day we are looking for. This is the take-home messages, and can make you happy. So this is the book that got already mentioned. So we are more than happy to receive feedback. Of course, this is just open access. So if you happen to be interested, just download the PDF from the MIT website. A couple of references, and again, I would thank all of you very much for your attention.
Please. No, you have something substantive to ask. I was really going to ask if you'll send us so we can check you out.
More than happy to. More than happy to.
So, when we talk about invariance, maybe then every time you can giving effect every time, right? Every time just select. And the conditional.
But this I don't see, because I mean, you would still have that.
Negative bias, right?
So you're saying that you have a difference. I mean, you're selecting on a different value in each environment.
You select x equals to y, in different endpoints according to different.
Yeah, so in the first environment, you say you choose the data points where y is close to 5, and in the second environment, you choose data points where y is close to -3. Yeah, so then or close to this. No, but the point is that if you say, I mean, if x is no, okay, so if x is causing y, okay, so basically what you're doing is, and this is the one thing that you're not allowed to do. So there I agree. You cannot choose the environment according to a descendant. This is, for example, why clustering would also not work. Because what you're doing here, I was a bit confused because we would call the x the y, right? Because you're using this as a target. So if y is causing x, and then you're doing a selection bias on x.
X causing y, and
Yeah, but your target is x. We always have a target in our method, right? That we want to infer the predictors of. And you're saying x given y is invariant. Okay, so let's say x is the target. It's fine with me. So what you're doing here is, and indeed this is the one thing that you're not allowed to do, you cannot choose the environments based on a descendant of the target. And this is what you're doing here, right? X is your target causing y, and you're selecting the environments based on a descendant. And I agree, this is the one thing that you're not allowed to do. Yeah. Yeah, but I mean, in a way.
I completely agree. I just
Go back now and
It would not, but also x given the empty set would not be different. So you would also accept the empty set. This would also be invariant. And this is, I think this is because the underlying idea is to use the heterogeneity in the data, right? And if this is not there, then it's actually good that the method doesn't say anything, right? So this is if you like, a proof of concept. I mean, yeah. So I mean, I just want to stress once more. So the underlying assumption here is really that the conditional of y given x does not change. And I have the impression that this is relatively robust against a lot of model misspecifications or against a lot of violations, but not against all, and it cannot be, right? So in a way, I don't think we will ever be able to infer, we will perform causal discovery without any assumptions. And this is the underlying assumption, yeah.
Yeah, I like the comment. All the biology experiment, all controlled experiments, and real world, those kind of things work on one cell line. You do one experiment. There are a lot of selection bias. A lot of times, this thing you observe, what on the variety of conditions, but on this particular cell it does not work. And so I think this is in biology setting, like what we do is if everyone have a different genetic background, but yet if nature preserves certain genes, and if you can observe the invariance between this particular gene and the other gene, it indicates that under all possible conditions.
I agree. So what you would like to do in practice, and of course this is something I don't spoke about here, but of course if you have many environments, you can then relax this assumption, right? So you can say maybe we are looking for models that are relatively invariant, maybe not over all environments, but over a majority. So you can relax this. You cannot relax this to an arbitrary extent. So if you're saying, well, it can be different in any environment, so everything it's actually a nice thought experiment, right? So if you assume that you're observing the data and in every environment, everything can change. So then I would say, well, okay, I mean, then that's fine, right? So we cannot do anything. So we have to somehow, and this is why I tried to, what I meant by anchor, we have to have something that gives us something to pull up to, right? So in this sense, if we can relax this to say, well, we are looking for something that is invariant over most environments, that's of course possible. It becomes a bit more tricky regarding computational issues, but this we can do. if we are allowing for arbitrary changes in all environments, then this method will not output anything. Yeah.
Would you allow that there to be a causal relation?
Yeah, this is, I think, the example that Kun had. No, let me see whether I have the because we also discussed this in the paper as well. So here, correct me if I'm wrong, Kun, but I think this is more or less what you also suggest, right? You have, I call this Y because this is our target, but it's exactly the same. So Y is causing X, and now we are clustering based on X. Right, so you call this a selection bias based on the effect. This is what you're not allowed to do. So this is what goes wrong. And this is you can generalize this. In general, clustering does not work, because then what you see here, this is exactly also what Kun said, right? So in this example, you have that Y will not be invariant, but Y given X will be invariant. So the method thinks that X is a cause, but it's not. And this tells you that you need to have some prior knowledge or something. So a lot of things would work. So you can cluster based on non-descendants, but if you cluster based on descendants, then this method really breaks.
Cluster.
That's fine. Whenever it's a whenever you have a variable where you are certain that this is a non-descendant of your target, you're in business.
Cluster.
That,
improve the power of your.
Yes. So this will be actually something very good. Yeah. So if you.
This would be like controlling.
Yes, exactly. Yeah. So this would be quite good. Yeah, we'll have a lot of signal. Of course, there's this mathematical game now that you can play to say, well, what are the most informative interventions, right? So it turns out that with the single interventions, in some cases, you can identify all the causal parents. And this is of course a mathematical game that you can play, or you prefer, or you just not play it. Yeah, to a certain extent it is. Yeah. So the point is always, what you have to do. Sorry for repeating myself, but this is really this. I'd like to show this version here. So it's really about you have to be able to know how to model Y based on XS, and for many feedback models, you know how to do that. So then that's fine. Also, if it depends a bit on what you mean by feedback, right? If you have the time component, even this is also what I mentioned earlier today. So we are now looking at ODE-based models where you actually have even time observation, and then in these models you often have feedbacks, right? It's also the same idea works. So as soon as you have an idea of how to model Y given XS, it can be like a linear model, a non-linear model, or we are now looking at ODE-based models. This is all fine. The only thing somehow you have to be able to say, what does it mean that my model works exactly the same in this environment, in the blue one and the orange one? And as soon as you have a test for this or can answer this, then you apply this idea to any model that you like. It depends on how strong the measurement error is, right? So if it's a very strong measurement error, I have the impression that you will again find not any invariance, because if you have this is, I think, if I understand you correctly, so you have something like this, right? So X, but now the point is that you're actually observing this, you're not observing, you're observing F tilde, and then you have Y, and let's say you have your environment or something X on Z, or let's say even X on X even or something. The point is, using X tilde, you cannot block the influence of the environment, right? So if you do not observe this, then at least formally, if you assume faithfulness, you will not be able to find any conditional independence here. So this is why I said my intuition is that if it's not so strong, then X tilde will be a good approximation for Y, and for finite many data, maybe you would find the independence. However, if it's a very strong observational noise, I have the impression that everything will get rejected. Good point. This measurement error are really like, so in the ODE-based system, it's like very difficult to handle. I mean, Kun also has some work on this, right? So. Oh, very. We don't expect this to hold many cases because this is why the extensions to nonlinear data are trivial, and this is what we would do in most situations. The example that I showed you, but this is, I think, pretty surprising. I mean, this is a linear model. This is genetic data, and it looks pretty linear, no? I mean, this is what we found with the linear model. So, and I think, we were at least surprised. But of course, in general, we don't expect this linear model everywhere. Yeah, but this kind of model misspecification, you don't have a problem with, because then you again would find that nothing is invariant. So these model misspecification, I think this is really not a problem, only in terms of power, but not in terms of level. Because then even if the true underlying data generating process is nonlinear, and you expect it's linear, then in general, what you would find is that you don't find invariant sets. Yeah. Yeah, exactly, but also not a wrong one, right? So at least you're saying, I do not know. Yeah.
I can do that.
Yeah. Yeah.
All right, thanks again.